she originally hails from Germany, where she did her PhD and I think part of her postdoctoral work also there. And then after some other postdocs, she's finally now a professor at the University of Sao Paulo, in the state of Sao Paulo. It's about 200 kilometers from the city of Sao Paulo. It's also named the University of Sao Paulo? Or what?
Yes, it's the University of Sao Paulo. It's a campus. So University of Sao Paulo. The university is very big. So they have a lot of campuses all over the state.
So she has done a lot of work on the areas of the ADO-CFT correspondence, and I think also on the topological solitons and related issues. And today she'll be speaking on the Gauss Bonnet interaction, on the properties of boson stars and hairy black holes. In fact, she's one of the experts on the boson stars also. She's done a lot on there also. And she's staying here for about 3 days at our center. But this is not her first visit. She came earlier to our city, I think twice.
Twice, yes.
Twice. And then she returns after a couple of days. So.
Thank you very much for the introduction. Yeah, I hope to come back many times. So, as said, I'm going to talk about the Gauss Bonnet interaction, and I'm going to tell you about the influence that this interaction has on properties of black holes and also on solitonic-like objects. I'm going to tell you a bit more about boson stars and black holes when I'm using the red one that seems to be working. So on boson stars and these black holes, and I'm going to say a bit about boson stars and the black holes as well. And as Professor Banerjee already mentioned, I've been interested also in the ADS-CFT correspondence and applications of that to condensed matter in particular. So I'm also going to mention a bit about these applications here in this talk. I'm going to turn to anti-de Sitter spacetime. So let me give you the outline of the talk. I'm going to give you a brief introduction, which questions I'm interested in this context. Then I'm going to show you the model that I've been using mainly, and in fact it turns out that there are some analytical solutions. I'm not claiming that I'm giving all possible analytical solutions. I give you some of the analytical solutions that are interesting in due course. And then the main bit of the talk is on my work, which is mainly on numerical solutions. So what I'm doing is solving coupled systems of ordinary and partial differential equations to get these solutions. And I'm going to tell you a bit about asymptotically flat space-time, where we have worked on boson stars, and we have tried to see what the influence of the Gauss Bonnet correction is for those. And then, as I just mentioned, there is also some work we have done on the anti-de Sitter space-time, and there are some interesting applications of these type of solutions that we have studied there. So let's start with the Gauss Bonnet action in these space-time dimensions. So if I just write down this action for the Gauss Bonnet term, then as you can see, what this action contains are second order terms of the Riemann tensor, the Ricci tensor, and the Ricci scalar. And there is a very subtle combination of these coefficients of these three terms, such that though you would expect that this has higher derivative differential equations resulting from it, it turns out that this combination leads to equations of motion which are second order in derivatives still. And that's quite nice. So this term does not introduce additional degrees of freedom into the theory, though you have higher derivative terms. Now in D equals 4 dimensions, so 3 plus 1 space-time dimensions, this term is not really interesting because it turns out that by the so-called generalized Gauss Bonnet theorem, this term here can be written as the total derivative of another term. I didn't write out the explicit version of this term, it's just enough to tell you that it's a total derivative. So the total derivative does not contribute to the equations of motion. Okay? So in 4 dimensions, that's not really interesting. So the lowest dimension that this becomes interesting is 5 dimensions, and that's the case I'm going to focus on in this talk. One more thing, the Gauss Bonnet coupling has the dimension of a length squared, if you think about it. So there's the square of the Ricci scalar in here, so the dimension of that should be length squared. And in fact, it appears and is motivated by certain string theories if you make the low energy effective expansion of these string theories. And you expand in this parameter alpha, which is proportional to the length of the strings, so the string length squared. And then you see, obviously, that's the dimension that's just right. Okay, so then I also mentioned to you that I'm interested in the anti-de Sitter case, so in anti-de Sitter solutions, or asymptotically anti-de Sitter solutions, I should say. And the question is, why am I interested in this, and why am I interested in the Gauss Bonnet term in particular? So, to state the gauge-gravity duality, this just tells you that if you have a d-dimensional gravity theory in an anti-de Sitter space-time, then that should be dual to the d-1 dimensional, to a d-1 dimensional SUN gauge theory on the boundary of anti-de Sitter. And this has been worked at by these people. The most famous example of this is the ADS-CFT correspondence, which has been used by a lot of people. And what one can see if one looks at the couplings relating these two theories, one finds that these couplings are related by these two relations. Now, imagine I'm taking the classical gravity limit. So what I mean with classical is that you don't have any quantum effects in there. Classical would mean that the string coupling that appears in string theory would tend to 0. So you are back to the classical limit of gravity, of string theory. And gravity is just the limit where the string length tends, in relation to the bulk scale that you have in this theory, tends to 0. Okay? So this limit would correspond just to standard Einstein general relativity. Okay, and if you then look at the quantum field theory side on the boundary of ADS, you notice that you can do this only when the n becomes infinite. Okay? And at the same time, the so-called tough coupling, which is the one that's important for these gauge theories, which tells you the strength of the coupling, becomes also infinite. So what you end up with is that general relativity is dual to a strongly coupled quantum field theory, where the rank of the gauge group in the theory tends to infinity. Okay, then you might say, of course, classical general relativity is reasonably easy to solve. So a lot of people have used classical general relativity to learn something about these strongly coupled quantum field theories. I'll mention an example later on in the talk. But of course you might say n going to infinity is not what we see. QCD has SU3, right? 3 is not really infinite. So the statement is, what can we do if we want to go away from the n going to infinity limit? If we want to take 1 over n corrections into account in this case. And what happens there, if you want to take these corrections into account on the quantum field theory side, then what happens on the gravity side is that you get corrections from this term, right? And that's nothing else but having alpha corrections. And the first alpha correction I just mentioned that appears in the limit low energy effective action of string theories is the Gauss Bonnet correction. So the Gauss Bonnet correction would be the first correction you would get if you would get away from the n infinity limit on the quantum field theories. So that's also motivation to study these kind of things. So the question that I'm trying to answer in this talk, and that I've been concerned with over the last years, is to see what this Gauss Bonnet interaction does to the properties of black holes, in particular in asymptotically flat space-time and in anti-de Sitter space-time. And then I've also been interested in solitonic solutions, for example, Boson stars. I'm going to come to this. If you don't know what Boson stars is, I'm going to mention what it is. Also in asymptotically flat and anti-de Sitter space-time. And then the question is, what does this Gauss Bonnet correction do to the ADS-CFT results, for example, the results on holographic superconductors? Is there any influence of this correction that is remarkable in this case? So I'm going to give you the model and some analytical solutions, as I already mentioned. That's the model. That's in 4 + 1 dimensions. So what we are looking at is Einstein-Gauss Bonnet gravity. So you have the standard action of Einstein-Hilbert action with a cosmological constant, which is negative. So we are looking, well, if you put lambda equal to 0, you are at asymptotically flat space. Here you are at asymptotically anti-de Sitter if it's non-zero. Then you have a complex scalar field here and here, which is coupled minimally to a U1 gauge field. You have a potential, which will also play a role later on. It's the scalar field potential. I will mention that later on. And then it's the Gauss Bonnet interaction with this Gauss Bonnet parameter alpha, with which you can tune the strength of the interaction. Yeah, so these constants are just given here. And as I said, I'm going to mention later on what's happening. The interesting thing is now that if you switch off the scalar field, which you would assume is the easiest field in this whole thing, you can find analytical solutions of this model. And this has been done for the case of so-called non-rotating solutions, static solutions, in which case I write the metric in the following form. I'm going to repeat the metric later on in the talk. So you parameterize the metric in terms of two metric functions, the f and the a, and then you have this part here. We have worked on different types of these planes here. So we have looked at the hyperbolic case, where this one here is some hyperbolic three-dimensional manifold. We have looked at the flat case, where it's just easy to write it down. And this is the spherical case, where this is just the metric of the series. The meta fields are chosen to be, we're just choosing the electromagnetic field to have a component in the electric field. You can extend this to magnetic fields, but just to show you the basic ideas, it's enough to do the electric one. And then we are assuming the scalar field to be parameterized like this. Okay? Of course, later on, when we have the gauge fields present, we can always gauge away this phase. Right? So there's a U1 gauge symmetry, so this phase can be gauged away and the scalar field will be real. But I'm just keeping this because I also want to look at the case where there are no gauge fields. Okay, so I just mentioned that you can find solutions to this model. I mean, this model is not simple, right? So if you take off the scalar field, then you still have the electromagnetic field, you have this part, you have the Gauss Bonnet interaction, but nevertheless you can write down explicit solutions to the equations of motion. And this is the famous Bourbadesa-Kai solution. So scalar field is 0, as I said. Then you write down the electric field, so you have this typical Q over R squared behavior. Notice we are in 5 dimensions, that's why electric fields fall off like R squared, not like R. And then the metric functions are, the metric function A is trivial, it's 1, equally 1. And then the metric function F has this behavior that might look very strange. So I'll just show you some specific cases. Let me just point at 2 or 3 things here. So this is the charge. And this parameter Q tilde is proportional to the Q. There are some factors that I didn't want to put. We'll have to adjust the length here and not add anything to this. The M is the mass parameter, so that's proportional to the mass of the solution. And then again you have the K here, so you can describe hyperbolic, flat, or spherical solutions. Now there are very specific, this looks really strange and unknown to most people who are not working in this field. You can find very specific limits of this, which are much better known. If you take away the charge and set the Gauss Bonnet coupling to 0, you end up with the Schwarzschild anti-de Sitter solution. So this looks like this. Right? So you have the typical mass term again, R squared, because we are in 5 dimensions, not in 4. And this is the typical anti-de Sitter part of the motion. Then you can also let the anti-de Sitter radius tend to infinity. You end up with the Schwarzschild solution. And again, there's R squared, not R here, because 5 dimensions. And you can also find a solution to this if you put the charge and the mass to 0 and the Gauss Bonnet coupling to 0, and you end up just with the anti-de Sitter solution. And this is exactly this one. When k is equal to 1, by the way, people call this the global anti-de Sitter solution. Okay, so there are specific limits in this case, which are going to be important later on at the talk. The interesting thing is, if you try to solve the full system of equations that result from this action here, as soon as you put in the scalar field, you have to do this numerically. I don't know why, I'm always stunned by this. You can do a lot of things with gravity and electromagnetic fields, but as soon as the scalar field, even a real scalar field, comes in, you have to do numerics. There are no analytical solutions. One analytical solution, though, exists, and that's something that we sort of recently published. So if you switch off the gravitational coupling, so you have a fixed space-time background, the space-time is not dynamical. You look at uncharged solutions and you put a specific potential for the scalar field, which is just the mass. Essentially, you have a mass term and a potential. And you look at the spherical case. The equation looks like that. It's very nicely linear. And what you can find, yes, and I should of course say you are in a fixed anti-de Sitter background, as you can see here. So it's just the R squared L squared appearing here. And what you can do is you can find a solution to this linear equation. And you can do this in terms of a basis in anti-de Sitter space, which is called the oscillon basis. And this oscillon basis is given in terms of hypergeometric functions. Okay. What you find is that then this omega that appears here is quantized if you require in addition that these solutions are regular. So these oscillons play a very big role in the study of the nonlinear instability of de Sitter. Then, of course, you would look just at a massless scalar field as a perturbation on the de Sitter background. But we found that you can also find the massive generalization of this, and that's what we sort of looked at in that work. Just to show you how these things look like, so here they are given. That's these basis elements, these oscillons that you have here. These ones here for the first three Ks, K0, 1, and 2. And what we have done, we have normalized the value at the origin to 1. You can always do that because it's a linear solution. And what we find are these we just plotted here. We didn't find this. This is what we plotted with some program. So you find k equal to 0 is a solution which goes from 1 to 0. Then you have k equal 1, which has 1 node, and then the 2 has 2 nodes. This inner figure here shows just the difference between the massive oscillons and the massless oscillons. They don't differ very much, but still there is some complications in the quantization of the omega. So I'm coming back to this and making the connection to boson stars later on. But as I said, these solutions are very important when you study the nonlinear instability of de Sitter, which a lot of people are doing at the moment.
Just a question.
Yeah.
Just to go to the previous.
Yeah, sure.
You see, you said that with the inclusion of the term for the scalar field,
Right.
it becomes difficult to solve with analytical.
Right, absolutely.
Except perhaps, I don't know, I mean, but is this the only possibility, or there could be other possibilities where you could solve it analytically?
I don't say that there are no analytical
You don't
solutions.
say that there are no other.
I just say that they have not been found yet.
There are
Yes.
Okay, so this is the
That's the statement.
only known example as yet
Yes.
of an analytical solution.
Yes. So yeah, people started off doing this with m squared equal to 0. They found this oscillon basis, and then we have generalized to m squared. But it's always in a non-backreacting case,
It's always
in a fixed de Sitter background. I'm not excluding that there are analytical solutions, which you can never be sure of. But I'm just always stunned because the scalar field feels like a simple addition to this thing. It's just the simplest case you can think of, simplest field you can think of. And as soon as you put it in, everything has to be a numerical. I'm always surprised by this, but that's the way it is. So maybe there are analytical solutions. Don't exclude it. It's not proven that there are. Okay, so we come to the numerical solutions, and I'm going to say something about the asymptotically flat space time first. And the first thing I'm going to say some things about Boson space. So I'm going to just say a few words about this for those of you who are not familiar with these kind of objects. They have been very popular 20 years ago, I would say, as really astrophysical types of objects. But now they have become again popular in the context of the de Sitter nonlinear instability. So what these things are made of are just scalar fields. You have a complex scalar field which you minimally couple to gravity. And then you have a global U1 symmetry in the system. So a symmetry in the system implies that you have a conserved current and a conserved charge, Hütte charge and Hütte current. So that's why these people often also call them non-topological solitons, because they have a conserved charge associated. They are lumps of energy that are located so. So you have a locally conserved Hütte current and a globally conserved Hütte charge, and the expressions for these currents and charges are given here. Now then, for the scalar field potential, there are different possibilities. The first possibility you can think of is just to put in the mass term for the scalar field. That's something you can do. There are solutions, and people normally call them minimal Boson stars, because that's the minimal thing you can do with the scalar field potential. But what a lot of people like, especially the group in Oldenburg or Jutta Kunz and these people, they like to put in this type of potential. The reason for this is that if you go to the flat space-time limit, then there exists one. So stating that if you switch off the gravity interaction, just look at the scalar field itself, then it's a model with a complex scalar field and just the phi to the 6 potential has topological type solutions. and these solutions are called Q-balls. So the nice thing is that in this case you really can turn the gravitational coupling down to 0 and you will still find topological solutions, which you would not have in this case. Okay? But then on the other hand, of course, phi to the 6 is not renormalizable potential and so forth. So what we have done is we have looked at what the Gauss Bonnet interaction does in this case, and that's one of the one figure which shows the results that we have found there. So what you see here is the Noether charge in dependence on the omega, which appears in the phase, and the e exponential ei omega t. And what you find, and that's not surprising, is that these solutions exist only in a given interval between some minimal value and some maximal value. As you can see here, so this would be the minimal value, and this is the maximal value. And then you see for small alpha, and this is exactly the same as in the case without any Gauss Bonnet interaction, you see that these solutions show the spiraling behavior. And it's very difficult to continue in this spiral here, but in principle what you would expect is that there are some spirals, and then there is the center of the spirals would be the value of the critical omega where the solutions stop to exist. So that's very similar to the case of in pure Einstein gravity. But what you also see, maybe I should just say this here. So what happens here is that these ones that show the spiral are the ones for either alpha equal to 0 or small alpha. And then what we found is that if you increase the alpha, the Gauss Bonnet interaction in this model, then this spiral sort of unfolds, right? So what you see at some stage is that there is only one curve which goes from omega equal to 1 down all the way to omega equal to 0. In fact, it's not shown that it goes to omega equal to 0 all the way, so the numerics here was extremely difficult. But we showed that the curves sort of all return back to omega equal to 0. So why is this the case? I guess one more thing that I should say is that if you look at all of these curves, they show a big difference here. But here they seem to all join into the same curve at omega equal to 1. Then you might ask yourself, why does the Gauss Bonnet correction play so much role here, but here it doesn't really care? And that's not very difficult to understand if you look at the limits that are appearing. So if you go to omega going to the maximal value of omega, which in our case is just omega equal to 1 here, then what you find for the scalar field profile is that it essentially spreads out all over space. People call this the thick wall limits. And if you go to the critical omega, so if you go in this spiral and come here, or if you go for the Gauss Bonnet all the way down to omega equal to 0, what you find is that this is more or less becoming a very steep function close to the origin, and then it's just 0. Okay? So what happens if you go from the maximal value to the critical value of omega is that this solution becomes narrower and narrower, more and more located close to the origin of the system. Okay? So there's a strong influence in the thin wall limit. Thick wall limit is not really important.
This is for the psi to the 6th potential, right?
This is for the psi to the 6th potential, yes, exactly.
So do you also have a plot for the ordinary psi squared potential?
No, we haven't done this, but we haven't published it, let's say. We have done it, but the differences are not big. There are not a lot of big differences.
See,
qualitatively, it's...
No, qualitatively there should be a difference because the psi squared potential will be linear equations, right?
Right.
So you can superpose the solutions.
Yeah, no, but the scalar field equation is linear, but there is
Right.
also the Einstein equation, which is
Yes,
not linear.
but
So-
you can,
So we always have gravity in here. So we are not
that is
looking...
minimally coupled.
Yes, but
So-
still, due to the nonlinearity of the Einstein equation, the whole system becomes nonlinear.
That's true.
So
But
you cannot write
you
it
can
down.
add over different values of omega. That's what I
That's
think.
possible. I've never looked at that in detail. That's true. Yeah, I mean there are some differences. What we have done is we have looked at the minimal boson stars in 5 dimensions with the m squared term, and we found that stability, for example, changes.
Yeah,
That's, for example, something that changes exactly. But we haven't really put in the Gauss Bonnet correction there. That's something we should maybe do at some stage, actually. Okay, and so this is now the same solutions, but here what we have plotted here is the mass of the solution. versus the radius of the solution. So this is in the context of applying this maybe to astrophysical settings. So what we find is that again, the spiral that you see here in this relation unfolds if you increase the Gauss Bonnet correction. And at some stage you really find the unique relation between radius and mass, which for example for the smaller alpha you don't have. So if you take, for example, radius 2, then you have 1, 2 solutions with different masses for radius equal to 2. While if you go to these solutions with higher alpha, you have only one solution. Okay, so it's a unique relation between mass and radius. And what you also see is that, of course, for a given radius, increasing alpha makes the mass of these solutions bigger. So the solutions have a bigger density. Right? So the density of these objects increases with increasing alpha. So the statement is that if you include the Gauss Bonnet corrections, these Boson stars can become denser than in the pure Einstein gravity case. So let me come to the asymptotically anti-de Sitter space-time. This is essentially most work that I've done on these Gauss Bonnet interactions. And the question is, why are we interested in this at all? So this goes back to the paper from 1982 by Hartmann and Friedman, which then was sort of known, but now it is extremely popular, this paper. So what they looked at is a massive scalar field with a given mass parameter m and a d-dimensional anti-de Sitter space-time, macro. So and then they were interested in studying if this anti-de Sitter space-time is stable if you put a scalar field or scalar field perturbation on top of this anti-de Sitter space. And what they found is that you find normalizable finite and conserved energy states of this massive scalar field only if the mass squared is smaller than this expression here, which is dimension dependent and dependent on the anti-de Sitter radius. And this expression is normally called the Hartmann-Friedman bound in d dimensions. So the statement, or to reverse the statement, so these two sentences say exactly the same, but just to reverse it. So if the mass is larger than the Hartmann-Friedman bound, then anti-de Sitter is stable with respect to scalar perturbations. And what is very nice, when you look at this proof, which is a few pages long, then you see that essentially this also applies to asymptotically anti-de Sitter solutions. So if you have a black hole, which is asymptotically approaching the anti-de Sitter space-time, this thing also applies there. Why? It's related to the boundary conditions on the UES boundary. This whole statement that Hartmann and Friedman have made in that book. Okay, that spawned a lot of interest in the last 7-8 years, I would say. And people have found that in fact black holes can develop scalar hair in anti-de Sitter. So if you take a black hole in anti-de Sitter space-time, you allow a scalar field to form, you see this under certain conditions. And the two cases are the following. So this is the famous paper by Luxer that spawned all the interest in holographic superconductors essentially. And what he realized is that if you charge the scalar field and you look at the equation for the scalar field, then you find that you can define an effective mass for the scalar field, which is the original mass you put in. But then there is also a term which depends on the metric and the gauge field. Right? And I explicitly put here the absolute value of GTT, not to have problems with the sign of the convention of the sign in this case. So what can happen is that so imagine you choose the m squared larger than the d-dimensional Hartmann-Friedman bound. Then asymptotically, ADS is stable. But now, close to the horizon, this term here, well, maybe I should say asymptotically, of course, this here tends to 0. It's just an electric field potential. Then, close to the horizon, this term here can become very big because of the GTT there. So what can happen is that even though this one is above the Hartmann-Friedman bound, the whole expression here can drop below it, close to the horizon of the black, if the curvature is strong enough. Okay? So then, close to the horizon of the black hole, there could be scalar hair formation. Okay? This is the suggestion, a simple argument, and of course you have to check numerically that this works. I'll show you an example in a moment. The question is, can you also do this with an uncharged scalar field? Do you need the electromagnetic field in there? And the statement is yes. So what you can do is if you have an extremal black hole, or near extremal black hole I should say, and you look at the near horizon geometry of this, what you find is that this near horizon geometry always contains a two-dimensional anti-de Sitter space factor. And then another manifold which has d minus 2 dimensions. Okay? At least this is true for all the cases that I know. Maybe there are counterexamples, but I don't know any. And so this is a two-dimensional anti-de Sitter. So, and remember, the anti-de Sitter bound depends on the dimension. Right? So what you can do is you can choose a mass that's larger than the d-dimensional brightness of the bound and smaller than this one. So the near horizon geometry with this ADS2 factor will become unstable, while asymptotically everything is fine. There is no instability. Okay? Show you two examples just to exemplify. Maybe I'll just say something about the properties of the black holes just to show you exactly what we have done. So we define the Hawking temperature and entropy. Entropy is, if you have the Gauss Bonnet correction involved, it's not just the area. There's an additional term appearing here. This is this one. And then the temperature is given by the metric functions on the horizon, essentially. And the V3 is the volume of the three-dimensional space. Specific heat is just this expression. If you are in the canonical ensemble fixing the temperature, then if C is positive, the black hole is thermodynamically stable. If it's negative, the black hole is thermodynamically unstable. And if I'm reverting back to the canonical ensemble, which I'm just going to do, then the quantity I have to look at is the free energy. Free energy is given by the energy minus temperature times entropy. Okay? This is the relevant quantity to decide which of these solutions is thermodynamically stable or unstable. So that's the first example. Remember that I said that close to the horizon of a near extremal black hole, you have this ADS2 factor, and then you would expect some instability there. That's exactly happening if you look at a solution that has a hyperbolic horizon but is uncharged. You probably know that if you just look at the Schwarzschild solution in ordinary space-time, and this has no extremal solution. It just has an horizon, that's it. Solution that has an extremal solution is, for example, the Reissner-Nordström solution. So if we want to get rid of the charge in there and just see really what the scalar field does, we have to go into the more exotic solutions. Okay? And this is the hyperbolic horizon. The hyperbolic case has in fact an extremal solution which has temperature 0 and the horizon radius given by the anti-de Sitter radius divided by square root of 2. So close to extremality, it has been shown that the horizon topology is exactly ADS2 cross a hyperbolic manifold, dimension 3. And what we have worked out is the anti-de Sitter 2 radius of this Gauss Bonnet black holes, which is given by this expression. Okay? So normally you would have R is equal to L over 2, and we found out that the Gauss Bonnet correction just appears in this way in this two-dimensional anti-de Sitter radius. So what we can do then is to look at a mass parameter that is between these two bounds to trigger the instability of the solutions.
So for, I mean, whether it is stable or unstable, you take that criterion which is defined something specifically. I mean,
This one here?
No, in the last slide,
Yes.
just go one slide back.
This
Yeah,
one?
so you have taken that as the criteria for stability.
No,
But see,
no. What we have done is I just put that. I don't exactly
you
know.
don't use that.
No, we
But
use
what is your criteria then for stability?
the free energy.
The
So
free
we are
energy.
looking. Yes, I'm going to show you a picture in a moment. Exactly. Here it is. So what we look at here are, so what we compare are the black holes that have scalar fields on them and the black holes that do not have scalar fields. So the black holes without scalar fields are these solid lines here, right? And these are the analytically given solutions that I showed you at the beginning of it. Okay, and then you have different curves for, this is alpha 0, then you increase the Gauss Bonnet to 0, Gauss Bonnet coupling to 0.1 and then to 0.4. These are the solutions. Compute the free energy in comparison, in function of the temperature. Okay? And then you do the numerics and allow the scalar field to form, and what you find is that if you decrease the temperature sufficiently, being close enough to extremality of the solutions, the scalar fields start to form. Okay? So this is essentially the value of the scalar field on the boundary of anti-de Sitter. So from here on, these scalar fields start to form. So you see these branches of solutions with scalar fields branching off from these solutions without scalar fields. And what you notice is that these solutions, if you look at the free energy at a given fixed temperature, then the free energy of these solutions is always lower than that of the solutions without the scalar fields, meaning that they are thermodynamically different. Okay? And that's the case in all these cases we have studied with different values of the Gauss Bonnet. That's one thing.
And I mean, this you do it through the free energy.
Right, the canonical ensemble.
Okay,
Because
so then you can say that the lower the energy, you call that more stable.
right.
compared to the-
Yes, so we have done this with the
Right.
temperature. We have also done this with the microcanonical
Now,
ensemble.
how does this compare with the other criteria? So, when you do the stability analysis by referring to the specific heat,
With the specific heat, I have to admit we haven't done it. What we have done is we have looked at the entropy as function of the mass. So that would be the microcanonical ensemble. So you will compare the fixed energy and we get the same result. It's exactly the same result. So that of course should be independent on the canonical ensemble you look at. Okay, and then the other thing you notice is that, so this is alpha 0, alpha 0.1, alpha 0.4. So you notice that the temperature at which the scalar field solutions appear decreases with increasing alpha. Okay? So the condensation of the scalar field gets harder if you put in the Gauss Bonnet correction, which is also something people have observed previously for other solutions. Now the black holes with planar horizon, I just sort of, this is a sketch of what the solutions look like, because there's always this irritation what the R coordinate means there. Of course, if you're on spherical, this is just the spherical coordinate, but it's not. So what we have in this case is a planar horizon. So the horizon sits here, where this one is the R direction, and these one are the remaining directions, X, Y, Z. Okay, so there's a horizon of planar structure. We have a charged scalar field now. We need this, because we don't have extremal solutions appearing there, so we need the other mechanism that Boson realized to be there to trigger the scalar field appearing. And for R going to infinity, you have the anti-de Sitter boundary and its planar. And you see this here, so this would be the boundary of anti-de Sitter at R going to infinity, and this is exactly where the dual conformal field theory is, the gauge field theory, quantum gauge field. The application that a lot of people have done is to holographic superconductors, and the question is why holographic superconductors at all? Why is this interesting? This is just to show you how one of these high temperature superconductors looks like. So the superconductivity of these materials is associated to these copper oxide planes. So the copper and the oxide are these orange and red ones, okay? And there are planes here. And when they measure this experimentally, what they realize is that these superconducting electrons are essentially two-dimensional. Right? So that's very, very crucial in these so-called cuprate superconductors. They have quite high temperatures at which they become superconducting. 92 is well above the temperature for liquid nitrogen, which is 77 Kelvin. That's already mentioned. And the interesting thing is you can measure the properties of these materials, and what you find is that the accepted microscopic theory that you have for standard superconductivity, which is BCS theory, stating that you have electrons forming Cooper pairs with the help of interacting phonons, is not valid. So if you make computations with this microscopic theory, they do not agree with the experiment. So what people suspect is that there is some strongly interacting mechanism going on there. So there's a pairing of electrons as well happening, but a very strongly interacting mechanism. Okay? But if you talk to condensed matter theorists, they don't really know what it is. Up until now, they don't have a microscopic theory to study this. Okay? So the idea of the people that brought up these holographic superconductors is that why don't we use the gravity side to model the strongly interacting quantum field theory on the other side? That's the basic scheme of these holographic phase transitions. So what you do is something very similar to what I mentioned just before for the hyperbolic black holes. you have a black hole above a given temperature which carries no scalar field. Then if you decrease the temperature, you form a scalar field. And you can, by computing the transport coefficients of these objects, you can see that this one here is an object which is a conductor, and this one here is a superconductor. You can also do this with solitons. In this case, it's not the temperature that drives this, because solitons do not naturally have a temperature associated to them, like black holes do. And you can also form scalar here there if you trigger, for example, the so-called chemical potential. Okay? So that's the complete picture of this. But this transition is very similar to the one that I just showed you for the hyperbolic case. The question is then, what happens if you include Gauss Bonnet corrections? Why and all would you want to do that? So if you are familiar with condensed matter theory, which I was also not before I started to do this, so I had to sort of study this as well, is that there is a theorem which states that you cannot have a spontaneous symmetry breaking in 2+1 dimensions at finite temperature. Okay, however, people have studied these holographic superconductors in 3+1 dimensions, going down then to 2+1, and they have been constructed in a number of papers. Okay. So the question is, what's going on? And then people have suggested that, of course, what you are doing on the gravity side is you are doing classical Einstein gravity, which would correspond to the n infinity limit on the gauge theory side. So if you would go away from that, maybe you can suppress the condensation. You can suppress the phase transition to the black holes with scalar. And of course, then the complication is that, as I mentioned at the beginning of the talk, Gauss Bonnet has only contributions in 5 dimensions. So what these people have done is they have looked at black holes in 4+1 dimensions without back reaction. So they had just a fixed background, and they looked at the scalar field condensation, and they found that they could not suppress condensation in this case. So what we asked ourselves is that if you really look at the full system of equations, taking the Einstein equations, or the gravity equations I should better say, into account, can you suppress condensation? And that's what we found. We found the answer, the simple answer is no, you can't suppress condensation. So the Gauss Bonnet coupling is limited between these two values. Okay. And what we found here, this is the critical temperature of these superconductors, and this is the Gauss Bonnet parameter alpha. And when you scale L to 1, this is the limiting value. It's not that we have stopped the calculation, that this is really up to you. And then for higher value, for increasing values of the gravitational coupling, just given here. So what we saw is that the effect was twofold. So first of all, if you include the back reaction, you lower the critical temperature. And if you increase the Gauss Bonnet correction, then you also lower the temperature. Okay? But we found that the temperature never drops down to 0. Okay? So there's a sort of exponential decay here. Okay? So you can state the condensation gets harder for larger alpha increasing, but it's not so fast. Okay? So neither back reaction nor Gauss Bonnet terms can suppress the condensation. Yeah.
What is the tuning parameter in right?
Yes.
For without back reaction, poke limit it is to infinity, and here you are taking some finite value of e.
Yeah, I mean the probe limit is either setting the g to 0 or e to infinity. That's exactly the same.
And here you are, setting e some finite.
For this one here.
For the probe limit,
Yeah, the probe limit is either g equal to 0 or e equal to
the blue
infinity.
line corresponds to the probe limit.
Exactly, absolutely right. Yes, g. This one here is the probe limit. Absolutely. Yeah, exactly. Because it's only the ratio of the scales in gravity and electromagnetism that matters, essentially. Okay, so I come to the black holes with spherical horizon. So we also did that. So this is just to remind you of the metric. So we have these two metric functions. So what we found for these solutions is that if you have, so what I'm showing here is the horizon radius, and this is the value of this scalar field of this metric function here at the horizon. So what we found for small alpha is that the solutions exist all the way down to RH equal to 0. So you can make the horizon radius arbitrarily small. Okay. So then the question is, if you have no horizon anymore, is that a soliton? Answer the question in the next slide. For large alpha, we saw that the horizon, with decreasing horizon radius, in fact, the A of RH turns to 0. So we were asking ourselves, is there maybe some extremal black hole there, or what's happening there? Right? So the first question is that to answer is for alpha equal to 0, it is indeed the fact. The black holes tend to their soliton counterparts in this limit. So you can see this here. The soliton is in red, and the black hole is in black for very small horizon radius. And you see that, except of course for the boundary conditions that you have here, which are different, you see that the solutions are essentially the same. The boundary conditions, of course, are something completely different in the two cases. But you can see this with looking at the masses of these solutions and so on, that this is really the limit that appears. Now for the Gauss Bonnet solitons with scalar hair, there are also these solutions. But now we found that if you look at the black holes and you let the radius of the horizon tend to 0, these no longer tend to the soliton solutions. Okay. So again, this is the soliton in red, the black hole in this black, and you see that the solutions are quite different, right? For example, look at the scalar field. The scalar field here for the black hole turns to infinity, while for the soliton it has a finite value. Okay. So these two solutions, this seems not to approach the solution, which we suspect is related to the fact that, of course, if you approach the origin of the coordinate system, the Gauss Bonnet interactions become very important. Then, to answer the other case, we also looked at whether extremal Gauss Bonnet black holes can support scalar hair, and the answer is no. And the proof essentially follows the proof of the Einstein gravity limit. It's very, very easy. You write the near horizon geometry in this type of factor. Again, the ADS2 factor and 3-sphere. You put in everything into the equations and calculate these kind of things. You have two variables here, V1 and V2. And these should both be positive. And what you end up with is this expression if you combine the equation. Okay? So in order for the sum here to be 0, of course, what you need is that either C prime, which is the derivative of C at 0, and or this term is, well, and this term is 0. Okay? So this one here is sort of ruled out. You can check this by the other equations that you have in the model. So the only possibility to fulfill these two is if when C is really 0 everywhere. So stating that the scalar field in the near horizon geometry should always be 0, meaning the extremal Gauss Bonnet black holes do not support scalar. Okay, just a few words about the boson stars, and then I'm more or less close to finish. So the massive oscillons that I just mentioned to you have a very important meaning in the context of boson stars. So what we did here is we looked at the massive oscillons. Remember, the massive oscillons are for the case where the gravitational coupling is 0. Now we switched on the back reaction, the nonlinearity, and what happens is that the modes mix now. But what we find is that if you look at the spectrum of these solutions, so this is omega here, this is essentially the mass in units of the de Sitter radius, and you see that this is the oscillon, these are the oscillons 1, 0, 1, 2, and the boson stars. So it's essentially what happens is that there is a sort of slight shift in the spectrum. Okay? But it doesn't look very different to what we had before. And this is now for the self-interacting case. So we also look at the full potential with phi to the 6. And what we find is that if you plot the Noether charge in dependence on this omega parameter, that here this limit corresponds to the de Sitter vacuum, because the Noether charge becomes 0, the mass becomes 0, so you're just left with the pure de Sitter vacuum, and then again you see the spiraling behavior that I mentioned. So it's very interesting if you look at that. So again, to state this, if the value of the scalar field at 0 is 0, then the whole function is 0, and you have m equal to n equal to 0, that's global de Sitter. Okay. So what you see here are the profiles of the boson star solutions. Just remember the oscillons, so they look quite similar. And this is decreasing, I don't know if you see this green line, but you see probably the blue and the red. So this is decreasing phi of 0. up to here. And then if you would put phi of 0 to 0, you would just have 0 for the scalar field, returning back to global anti-de Sitter. Now it's interesting to note that global anti-de Sitter is linearly stable. This was shown in this paper. So we would expect that the solutions that are connected to the global anti-de Sitter vacuum are linearly stable. So there's some arguments from catastrophe theory that tell you that if you have solutions on one branch, they would not change the number of stabilities or instabilities. So the Boson stars connected to the anti-de Sitter vacuum would be linearly stable. So all these solutions here would be stable. And then as soon as you have this cusp here, just turning around, the number of instabilities increases. So the ones on the further branches are likely linearly unstable. So these are my conclusions. So the Gauss Bonnet interaction influences mainly the space-time close to r equal to 0. I showed you this for the solitons that I have, for the boson stars. And then remember that also we had this property that if you set the horizon radius to 0, then you, in the Gauss Bonnet case, you don't really end up with the soliton. So there's something crucially happening there at r equal to 0, which is sort of natural because it's the next correction that appears if you have higher, if you look at the low energy effective action of string theory, so you have a length scale in there. So that's what we showed in this paper as well. So we have also looked at rotating boson stars. I only spoke about the non-rotating ones in my talk. You can also look at rotating boson stars, and what we found is that if you take the Gauss Bonnet correction together with the rotation of these objects, there's also something interesting happening. Right? So you have the rotation axis, and the boson star rotates around this, and the Gauss Bonnet correction alters the behavior close to the rotation axis. With increasing alpha, the Gauss Bonnet black holes become unstable to form scalar hair at decreasing temperatures. This has been applied to mainly to holographic superconductors, but it's also interesting, as I mentioned before, in the context of anti-de Sitter. Gauss Bonnet black holes, when they exist, seem to be thermodynamically preferred. That's what we have checked with the canonical ensemble. And extremal black holes do not support scalar hair. That's my last transparency now, really. So oscillons and boson stars, I already mentioned that, play an important role in the study of the nonlinear instability of anti-de Sitter. And global anti-de Sitter seems to be non-linearly unstable for arbitrarily small initial data. I should say all of this here is numerical work, so there's a strong debate still going on about this statement. And the interesting thing is that if you look at the boson stars in anti-de Sitter that I just mentioned to you, that these are non-linearly stable. Okay, that's very interesting. Because this one here is just a simple limit of these ones here, setting the value of the scalar field function at 0 to 0. Okay, so these are unstable, these are stable. Non-linearly stable and unstable, I should say. And then, just as a sort of last thing, very compact rotating boson stars also possess an ergo region. So this is something that people already noticed before. And what we did is we also checked what the Gauss Bonnet interaction does there, but it seems to have just very little influence. Because again, we would expect the Gauss Bonnet interaction to be important, close to the origin of the coordinate system, close to R, at small length scales, and normally the ergo regions sit at larger R. So the Gauss Bonnet interactions does not really influence this ergo region. That's it. Thank you very much for the attention.
So if you have any comments or questions, you can ask.
Okay, see, basically, apart from the Einstein time, we have this Gauss Bonnet correction.
Right.
But why does not do other sorts of corrections?
That's exactly what we are just discussing. Yes, we had a project with a PhD student and so on to really go to higher corrections. So if the problem is only that if you for example stick to 5 dimensions and you put in the higher corrections, the differential equations you end up with are not second order. So you put new degrees of freedom, but then you have to go to higher dimensions.
Yeah, but
that's not a problem.
That's not a problem. That's what I thought.
Yes, exactly.
That's not a problem.
No, I don't think so. So, for example, if you want the third order correction, you have to go to 7 dimensions with Love-Log gravity. Yeah, nobody has studied this, but it would be very interesting. Yes, I would like to see that actually.
Okay.
That's the one. Yeah.
So okay, if there's no further question or comment, let's thank the speaker once again for a very nice and informative talk.
Thank you very much.